Assalamualaikum everyone. Let us continue with casting 6. So for casting 6, the topic that will be covered is shrinkage in casting. Now let us go to the shrinkage during the solidification. So most of the pure and alloys shrink during the solidification from the molten state, except for cast iron. This is because of the high carbon content in the cast iron. Instead of shrinking, it will expand due to the crystallization of the carbon. So graphitization during final stage of freezing cause expansion and counteract volumetric decrease associated with the phase change. So there are three stages of shrinkage. One is reduction due to the decreasing of pouring temperature, or we call it liquid contraction, and then reduction during solidification. This one is solidification shrinkage, and the last one is reduction during solid state cooling, what we call as thermal contraction. Now let's see in terms of the illustration. So at 0, starting level of molten metal immediately after the pouring. So this one, the first picture showing that right after the pouring. And then number 1, reduction of level caused by the liquid contraction during the cooling. So it will start to decrease in terms of the level of uh, the molten metal, because the metal start to solidify. Then the second one, again they are going to start with the reduction of high of this level of the molten metal due to the shrinkage, and at this level the shrinkage cavity will start to happen here. Okay, so because this is the solidified area, there will be some molten metal and there will be some shrinkage cavity. So at the end, further reduction in volume will cause thermal contraction during the process. So if you can see, there will be shrinkage in between the molten metal and also the wall of the cavity. Okay, so then at the end, after everything is solidified, there will be shrinkage cavity. So that's why in the normal casting process, they design the riser in order to supply the extra metal to this area. So if you want to associate with the graph for the solidification, it can be seen like in the picture. In the casting, shrinkage is not favorable. So solidification shrinkage need to be managed, usually by using the riser. So riser will compensate the extra molten metal into the cavity, so then it can prevent the shrinkage. And then for thermal contraction, usually we have to make a larger mold so that we can allow um, meaning that reduction of that shrinkage, then you're going to believe with the actual dimension that you want. So the allowance to compensate solid thermal contraction shrinkage is calculated linearly. So the shrink rule formula, if linear shrinkage is A, then for any length L, the compensation length is equal to L times 1 over 1 minus A. Okay, so if you can see from the table, the typical linear shrinkage for each material is presented in the table below. Now, let us see the shrinkage problem. Determine the shrink rule to be used by mold maker for die casting of zinc. Using the shrinkage value in table 10.1, express your answer in term of decimal mm of elongation per 300 mm of length compared to a standard 300 mm scale. So meaning that how much you want to elongate the design of the mold. Okay, so let's say for the for the zinc, shrinkage is 2.6. This one you can refer to the table back in the previous slide. So this linear contraction will be 1.0 minus the 0.029. So meaning that 2.6 divided by 100, so it's equal to 0.029. So you get 0.974. Then string rule elongation equal to 1 over 0.974 equal to 1.0267. So that the elongation supposed to be 1.0267. You times the 300, then it's supposed to be 308.008 mm. Okay, so the mole length supposed to be elongate to 308.008. So elongation for the mole is 8.008 mm. So here is another problem. So you try to solve it on your own, and the answer is already given here. So you can try on how to solve the question. To minimize the effect of shrinkage, it is desirable for region of the casting most distant from the liquid metal to freeze first compared to the one where the molten metal is poured. Okay. So meaning the farthest area is supposed to freeze first compared to the one near to the molten metal. So thus molten metal is continually available for the riser to from riser to prevent shrinkage void. So this term we use as directional solidification to describe the aspect of freezing and methods by which it is controlled. As I've mentioned previously, so to achieve the directional solidification, Shvorynov rules is used to design the casting process. So, for example, locate section of the casting with lower VO over A ratio away from the riser so that freezing occur first in this region, and then liquid metal supply for the rest of the casting will remain open. Okay, if not, the area when the area is freeze first, and then the area behind that part that already solidify will not get enough molten metal from the riser. So another method is by using chill. So internal or external heat sink that cause rapid freezing in the certain region of the casting. So external chill is usually used to encourage rapid freezing on a molten metal in a thin section of the casting. So the picture inside here showing where the external chill is placed, which is inside the sand mold instead of the inside the cavity. So this area will help to freeze this area faster, so that there will be no shrinkage cavity inside the part. So B is showing the possible shrinkage cavity that can happen inside the inside the product. So in the other hand, internal chill is a small metal is placed inside the cavity. So for example, this is the cavity. You place the chill, the internal chill inside that cavity instead of inside the sand mold. Okay, so this one, the internal chill, usually the composition of the internal chill is the same with the metal that going to be poured inside the cavity. So this picture shows the difference where the internal and also external chill is placed. So riser is a reservoir in the mold that serves as a source of liquid metal for the casting to compensate the shrinkage during solidification. So the riser must be designed to freeze after the main casting in order to satisfy its function, as I mentioned previously. So the shape of the riser normally will design to maximize the V over A. So meaning that we want the A value to be small and instead of big, so that it can solidify later than the cavity. So more constant, same with the casting and riser. So that's why it doesn't have any effect. So that's why the A is the most important thing when you design the riser. Here is the example on the riser design problem. Okay, so you can try to solve this problem. The solution for this question is given in the next slide. If you have any problem understanding the example, you can contact me. Okay, so there is also another question. Solve it on your own, so you can try to solve with the same methods how it's used in the previous example. So that's the end of cutting 6. Thank you for listening. Assalamualaikum. See you in the next lecture.